Hey, physics students. We're going to be talking about two different topics this week. We've got springs and we've got something called moment of force or torque. And these two things work together to kind of show us that how we apply a force matters just as much as how much force we're applying. So for our first concept, when we're dealing with springs, the first thing we need to know is that a spring is really anything where there is a restorative force that tries to make something go back to its original shape. Anything that does that, we can really treat the same way that we treat a spring. So even if it's not, metal like this spring right here, we could still be talking about things like rubber bands, and the way that they function is basically the same. Now, springs come in all sorts of shapes and sizes. I've got this little basic one right here. I could talk about like a really large spring, like something maybe out of a motorcycle. This right here is a shock absorber from a motorcycle. And we can go all the way down to the other end of the spectrum. And this is a slinky. And it doesn't do a very good job of kind of putting itself back to its original shape, but it does try at least a little bit. So all three of these things are springs. And so there's a couple of things that we should really understand about springs. And the first one is that all of these things, if we try to change their shape, will attempt to go back to their original shape. So if I stretch this thing out, it's going to apply a force to go back together. It's kind of going back towards the middle. So the moment that I let it go, it zips back to its original shape. Now, we can kind of figure out how much force we can apply to things. And let's make a couple of obvious statements here. If I put a weight on the end of this spring, it stretches out. And the more weight that I put on the end of this spring, the more it stretches. And while most of you are sitting at home, you're like, duh, Coltman, why are you telling us this? It's important to realize what's going on here because the amount of weight that we are putting on the spring is changing the displacement of the spring. And it turns out that the amount that displacement changes is actually mathematically consistent. So if I have this one right here, which is 500 grams of force, or a half kilogram, it stretches it out by that much. If I take these two things together, this is 250 grams, so a quarter of a kilogram. It stretches it out half as much as it was stretched out when this one was applied. So the amount of weight that I put onto it determines how much it stretches, and it's proportional. Now, that's easy to see with something like this. With something like this, even a little bit of weight will cause it to fall apart, like gravity causes it to automatically stretch. So that's not a super great example. And this one is so sturdy that no matter how much force you attempt to apply to it, it doesn't change. It changes a little bit, I should say, but it's not really noticeable. So those are just some general facts about springs. Now, springs follow what we refer to as Hooke's law. And just to let you guys know ahead of time, I hate teaching Hooke's law. And the reason that I hate teaching Hooke's law is that Hooke's law is stupidly obvious. And I really don't think anybody should get credit for an idea that is so obvious as Hooke's law. So Hooke's law basically states that, just like what I was giving an example, the amount that a spring will stretch is proportional to the amount of weight that I put on the spring. So if I have 500, it stretches by 4 centimeters or something like that. If I use 250, it'll stretch by only 2 centimeters because that's half as much weight. And that's literally Hooke's law. So there's an equation that you'll find in the notes for Hooke's law. It's important to understand the equation, but mostly it's important to understand the concept that the amount of weight or the amount that a spring stretches is proportional to the amount of weight that is on that spring. So that's kind of the big idea behind Hooke's law. Now, one of the things you will find in Hooke's law is a value for a variable called K. And K is referencing the spring's constant. And the higher your K value is, the more difficult it is to change your spring. So this, for instance, is really, it's a lousy spring. It doesn't even want to go back to its original shape most of the time. This would have a really, really low K value. This definitely is kind of our middle of the K values. It wants to go back to its original shape, but I can pretty easily stretch it with my hands. This has a really, really high K value. No matter how hard I try, I'm never going to be able to noticeably stretch this thing out. In fact, you would have to stand on this thing in order to get it to noticeably compress. So the K value determines how stiff a spring is going to be, how difficult it is to change a spring's position. And so that's kind of the basis of Hooke's law. Now, there's one other thing that Hooke comes up with, and again, it's so obvious that I really hate teaching it, but here it is. Hooke creates this idea called the limit of proportionality. It's a really fancy term, but really what it comes down to is, at some point, a spring will no longer stretch in a proportional way. And if I continue to put this into more common language, at some point, springs break. If I put way too much weight on this spring, at some point it will deform, it'll stretch out to a point where it doesn't go back to its normal shape. And that happens all the time with things like slinkies. In fact, you can see right there at the very top, that's what happened here. It has deformed a little bit. It didn't come like that from the factory. And when a spring deforms, it's never going to stretch the same way ever again. And so that is the limit of its ability to be proportional. So Hooke called it the limit of proportionality. You might see that phrase pop up on a test question. But really, all it comes down to is after you've hit your limit of proportionality, your spring breaks and it will no longer function like it used to. So that's springs in a nutshell. Not too difficult to understand. The next thing that we're going to deal with is an idea called torque. This thing right here is spinning, and it's spinning because I applied a torque to it. Now, we have a British science curriculum. Cambridge is a British science curriculum, so they might refer to this as moment of force. But here in the United States, we typically call it torque. And the idea behind torque and moment of force is simple. If you want something to rotate instead of simply move, you have to apply a force that is somewhere away from its center of gravity. So the center of gravity for this one is right here in the middle. And if I push this at the center of gravity, it shifts like this. But if I direct a force on this thing that is not going through the center of gravity, say out here, it won't move, it'll instead rotate. And so this is what we call rotational motion. It's not going anywhere, left, right, up, or down. It's simply spinning around with a point called the pivot. And you guys will have to identify the pivot at some point. But it's really just kind of important to understand that what happens is that we've got a rotation around a single point. And so this is rotational motion. Now, the important thing to know about rotational motion is that the amount that it rotates is based on two different factors. One, and the obvious one, is that I can make this thing rotate faster if I push it more aggressively. If I apply more force to it, it'll spin faster. Now, the other thing that you need to know is that how much it spins depends on where you apply that force. If I apply my force right here, really close to the pivot, it barely moves. If I apply the same amount of force out here, really far from the pivot, it moves noticeably faster. So how far away you are from the pivot determines the amount of torque that you generate. So think about if you were hitting something with a hammer. Let's pretend this is a hammer. Okay, some people don't trust their ability to swing the hammer. If the hammer head is up here, they grip it right here and they kind of tap things into place. It might work, but you're not generating a lot of force with it. With the exact same hammer, if I grab it at the end and swing it, I'm going to generate a lot more force. In fact, probably 3 to 4 times as much, depending on how large your hammer is. And that's because the pivot, when I'm swinging the hammer, is my wrist right here. This is the thing that is rotating around. So if the pivot is my wrist, the thing that is doing the work is the hammerhead. And the distance from the wrist to the hammerhead is the arm of that lever. It's what determines how much force I'm going to generate. When I'm holding it up here, the distance from my wrist to the hammerhead is fairly small. But when I'm down here, this is a larger distance, so I'm going to generate a lot more force. And if I was to swing with my elbow like this, now my elbow is the pivot. It's the thing that it's rotating around. I'm going to generate even more force. So torque depends on how much power you're putting into your swing or how much force you are applying and how far away that force is from the central pivot point. Now you'll find another equation for torque that's in the notes as well. The last thing I kind of want to mention is this idea of balance. Balance only happens when there is an equal amount of rotational force on both sides of things. So if I hold this like this and let it go, it is balanced. And what that means is that the amount of force being generated from gravity on this pulling it down is equal to this side over here trying to pull it down. They're balanced. If I was to move this pivot one way or the other, it wouldn't be balanced anymore. It would simply fall over. So you can find the balance point of an object, and where that is will tell you exactly how much force is going over here versus here, because you know they have to be equal. So that is moment of force and torque. And those are the two main concepts that we're going to touch on this week. So let's kind of go over what I'm expecting from you guys for this week. You're going to have to do a section of notes. That'll cover both springs and moment of force or torque. So those two concepts will both be together since they are fairly short. The other thing I'm going to ask you guys to do this week is a short discussion post involving springs. You'll have to identify some springs and talk a little bit about whether you think the elasticity is high or it's low, whether its ability to go back to its original shape is high or low, if you want to put it that way. After that one, at the end of this week, there is a Flipgrid video where you're going to be talking about moment of force or torque. You're going to be identifying an object around you that takes advantage of moment of force or torque, and you'll have to identify the pivot as well as the arm. So you'll be talking about where the pivot is and how far away the force is being applied from the pivot. So that's kind of our assignments for this week. If you're an online student, you'll also find an additional assignment since you won't be with me in class except for on Wednesday. You guys will be doing a balance act simulation. So basically it's kind of a game that forces you to balance different things. So that is this week in a nutshell. Hopefully you'll find this video to be kind of a good way of getting things started. It wouldn't be a bad idea to start the notes ahead of time. Otherwise, you're going to wind up doing them all in one day. So good luck, and if you need any questions, feel free to email me. If you're in person, I'll see you on your day in class. And if you're online, I'll see you on Wednesday.